Hello, everybody. Good afternoon. Welcome to today's Liftoff webinar. My name is Christine Longroy, Vice President of Business Development here at LIFT. LIFT is the National Advanced Materials and Manufacturing Innovation Institute headquartered in Detroit. We're thrilled to have our LIFT member, EOS, presenting today. At LIFT, we're focused on strengthening the defense industrial base, connecting, convening government, industry, and academia, where we advance manufacturing through technology and talent development with a core mission of ensuring the transition, scale up, and fielding of advanced materials and processes that support our nation's economy and security. Today, we have a great presentation with Dr. Yash Parikh, process engineering consultant who's got over a decade in additive manufacturing and bridging that gap, as we talked about. He secured over $5 million in funding to actually develop this. And I would like to turn it over to Yash. Thank you so much for joining us today. I'd like to remind the audience during the presentation, please put any questions in the Q&A. We'll get to those at the end. So take it away. Thanks again.
Thank you, Christine. Thank you, LIFT, for this opportunity to present our work with this Liftoff webinar. I'm pleasure to be here. I'm excited about this. My name is Yash Parikh, and I'm a process engineering consultant at EOS. Yeah, go to the next slide, please, when you're ready. Yeah, so funding acknowledgement goes to LIFT, America Makes, NCDMM, NIST, and so many others to fund this journey of bringing some newness to qualification. I have had colleagues who have supported some brilliant students and collaborators. Next slide, please. So a little bit of background. Christine did mention about my 10 years of additive experience, and that comes from my powder bed fusion based thesis work that I did during my PhD at Texas A&M. And then a one-year postdoc, I was able to do some AI integration with AM at Carnegie Mellon as well. And in my past life, I was assistant professor for 6 years almost, and I've taught like 2,000 students, some 13 different courses from basic mechanical engineering to product design to AI, and all of it in between. So I'm really excited. If I don't shut up when the clock turns 1 hour, that blames my previous experience as professor. Go to the next slide, please. So I've kept it pretty simple here. I'm gonna talk about 2 to 3 minutes about EOS for the audience who have not heard about us, and that's totally fine. Then another 5 to 10 minutes about qualification, and then most of the chunk of the talk is going to be about qualification, expediting it with the use of AI, in-situ process monitoring, and closed-loop control. So go to the next, please, when you're ready. So everybody knows EOS. If not, EOS stands for Electro-Optical Systems. We are the machine manufacturer of laser powder bed fusion systems. On your screen, you see 2 different types of systems. On the left-hand side, you see a metal system, M300 with 4 lasers. And on the right-hand side, you see a P system, a polymer system. The cost anywhere ballpark for metal system ranges from $750 to $1 million, all the way to $5 million, depending on the upgrades. On the polymer side, it starts around $250,000 to somewhere around $500,000. So go to the next slide, please. So EOS has been a global company, started in 1989 with just 4 employees when I was 2 years old. And that green dot that you see on the screen is the headquarters in Kreiling, Germany, just up north of Munich. And then the company expanded its business portfolio in North America with 2 branches. The red dot you see at 2 places. One of them is in Austin, Texas. The other one is in Michigan, in Novi. We are very close to LIFT, actually. From 4 employees in 1989 to a 1,500 employees strong, we have presence in Asia, in Australia, in Europe, and over 5,000 systems have been sold globally, out of which around 2,500 resides in North America. So every other research paper talks about research conducted on EOS systems, and it's both a moment of proud for us, and at the same time we take a lot of responsibility to be upfront on our research side of things as well. So from the revenue that we generate, 10% goes back to R&D. And just last point here is global business is between 55-45 in metals and polymer. And if you ask me about North America, it's more like 70-30, with 70% on metals. Go to the next slide, please. So that's all enough of EOS. Let's talk about qualification. If you go to the next slide, I was pondering upon this question. I said, I'm right now actually in DC, and I'm part of AM coalition, that we are meeting all the senators and all of that. And I was just pondering upon this question. I said, what are the key issues that are preventing a wider adoption of additive in general? And it's beyond LPBF. And I asked this question to a large language model that spit out a bunch of written information, all those OpenAI, Cloud, and Anthropic. And then I used this website called Create Word Cloud. And what it did for me, it kind of intensified the repetitive words. So the predominance of qualification, certification, that it stands out, tells you that all those texts that AI generated talks a lot about these issues. And I can talk about these for an hours and hours on certification, qualification. In situ is somewhere there, buried in there is AI, data, repeatable is a big issue, right? So go to the next one. Why is it so? Take a look at this example. On the left hand side of your screen and right hand side, you see the two different aspects of why qualification is a challenge. On the left hand side, you see a titanium 64 made additively manufactured laser powder bed fusion made cycle, tested so many times before they decided to put it for Olympic use in 2020. It failed during the race, right? The fatigue actually kicked the person out from the race. And on the right hand side, you see a thermal mismatch was studied by NASA. They looked at the interface temperature difference, interlayer temperature difference, and they paused the build for a couple of minutes. And they wanted to see what happens then if you resume the build. And I believe I have a video for this. It should be able to play. Go to the next one and I'll talk more about it. Take a look at this video. All right, so that happened. I don't know if audience were able to hear the sound of it. If not, that's what you got. Next slide, please. And you see, this was printed on our EOS M400-1. Four cylinders were printed like that configuration that you see on left-hand side of the screen. And this was printed on GR Cop 42. And I was telling you, as they wanted to see the thermal mismatch. Again, the laser powder bed fusion process, solidification rate is 10 to the power 4, 10 to the power 6 kelvins per second. They stopped the process in between and then restarted it. What came out is the build interruption, and the witness line formation on the extreme right. Right below, you see a witness line showed there, and which has a lack of fusion porosity. That was the key reason for the failed part during the testing, that you can see on the middle screen how it kind of progressed. So go to the next one, please. So, and this is the reason. The laser powder bed fusion process itself is very complicated. You see on the left hand side, you have a top view and the side view of the process. It's like laser is shooting on a powder bed and making it so much volatile. Then on your right hand side, you see a lot of things happening simultaneously. There are process parameters. There are things that are happening around the spatter, the balling phenomena, the formation of the gas spores, and so many other things going on there that influence the outcome. You see the rastering pattern of the laser on the powder bed. Powder size distribution changes if you reuse it so many times, and you have a different behavior altogether. If you're using multi lasers, then one laser's suit is in on the way to the others, and so many other things going on. So there is joke in the community. It says your chances of a defect free part is less than your chances of winning a royal flush. So yeah, that's a reality. If you go to the next slide, please. And people think to only care about from the qualification, from the build quality. Right at the center, you have a building process, but you got to know the whole value chain of laser powder bed fusion to understand and make sure the parts are repeatable and reproducible, not just off of a build plate, but you need to know the incoming inspection of the powder. You need to be wary about the powder size distribution. You need to know about the warehousing, where are your humidity control, what kind of storage conditions you have, how does the machine is going to be getting set up. If you change the material in between, how neat is your material swap. Everything matters is what I'm trying to tell here. Most of the time, the post-processing steps are the most important factor to the final performance of the part, because they are derived from the welding casting literature, and it does not do the justification to the laser powder bed fusion made part. So there is that. The fatigue behavior changes significantly if you have a different surface finish done on those parts which are off of the build plate. Go to the next one, please. Here's an example. We live in 2026. This is an example very relevant to this date. One of our customers has given us this image of how do they do qualification. And it's mind-boggling to see that one of the requirement to prove qualification is all IQ, OQ, PQ. And just to get you some understanding of IQ, OQ, PQ, because people talk about IQ, OQ, PQ, MQ, and it gets confusing. What you're looking at is once the machine is made, and let's take an example of EOS, machine assembled in Germany, they run a test called factory acceptance test. It gets all the line checks done on it, and it's like thumbs up, it's good, it has passed its initial verification. It gets shipped to a customer in the United States. They run the same job which they have done at FAT, factory acceptance, and now it's called site acceptance. And then they compare, contrast the results, and now it is called initial qualification or installation qualification ready. Once you do the IQ, you now go towards OQ, and this is one of the build layouts of OQ. But what they are looking into it is they want to see the entire build volume needs to be qualified for certain mechanical performance. This could be fatigue, this could be a static tensile, this could be creep, this could be corrosion. The samples vary on the end application, which is the part qualification. So literature exists. They tell you got to test out this sort of layout, and it's not good in terms of cost, in terms of time. If you go to the next slide, it tells you some of the numbers that are available in the literature. This image and the numbers are taken from the reference below. It's a paper published, and it tells you that from the coupon that you saw previous slide is anywhere around that ballpark. Of course, it varies machine to machine, envelope to envelope, criticality of the part, material utilization. What are you trying to qualify? Because it's complicated term. Qualification is the door hinges qualification requirement, subsequent issues that when it fails are different than something around nuclear. So these numbers, you have to just take it in a way that, okay, this exists in a varieties of application, and they just don't go on application to application. But this is just to get you a ballpark. And those on the audience listening to this, they need to know what qualification means in a simple word. So when I talk about qualification, it says demonstrating the process is reliable and repeatable no matter how many times you print that part and where you print that part, who prints it. That is about qualification. And certification is about gathering all the data that you just did for qualification and giving this to a certifying body to make sure that they authorize your application to make that part. Could be an implant, could be a sporting good, anything like that. So that is all about qualification. So go to the next slide, and I'll, as promised, this is my last slide on qualification. The topic that I'm touching upon is AI, in-situ process monitoring, and closed loop control, which is the next generation of the approach for expediting the qualification burden. You see on the left-hand side, there are like two different approaches. We talked about the disadvantage of doing this test pooling type of thing, and it just costly, time consuming, doesn't really reveal the true nature of qualification, but you do it because that's what people have been doing. On the equivalence qualification side of thing, A is equal to B, kind of B is equal to C, and then you deem A is equal to C. But that's a lot of engineering judgment there. What industry has been utilizing in last, I would say, 5 to 10 years is reliance on ICME approaches, digital twins, a lot of emphasis on previous data. Take a look at EOS, for example. We have 35 years of making machine experiences, right? So we have all the factory acceptance test data on all our printers. Maybe that's a good starting point to take those data and understand where printers are, how their distribution of certain mechanical properties within the envelope exist. And then the newness is the in situ inspection. People have tried those, but how do we do it for qualification? So go to the next one. So next 40 minutes, there are about 60 slides on this. Let's see how many we can cover. Go to the next one. Okay, so concept lies on signature. What you see here are, if I ask you to draw your signature, like physical signature, and ask you to ask somebody sitting next to you to do that, you can immediately say that that's not my signature because it doesn't have the uniqueness that you only can bring on your signature. So that concept has been executed in the next few slides. How the execution starts with running a nominal jobs. The nominal jobs could be a configuration that you keep constant, because remember, qualification is all about making things fix and then understanding the variation afterwards. So you define a nominal job, and I'll show you some examples of it, and then you run it a couple of times. How many times? I would say 3 to 5 times would be a good ideal starting point. What you would see out of this is all the differences that you can get from running the same job so many times on the same machine, on the same layer thickness, on the same material. Of course, the differences are because you are now sieving the powder. You have a 67-degree scan rotation. You are utilizing a different placements. All of that matters. And then you get an identify a signature that you think that is an appropriate representative of this part or a build job. And then you start to specify the limits on which is demonstrated in the pink color. The upper and the lower limits are a tough thing to establish. These are like a $5 million JMAT type of an affair, where you really need to know anything below this is bad, anything over this is good 100% of the time. And that requires a lot of testing. And that's where the AI sort of part comes along. And if there is something goes off, you just deem it not okay in a terms of law. It's not a failed part, but you need a secondary measure to kind of retest it some way or the other. So next up, next one, please. Yeah. So first thing you do is you need to know how many types of modalities exist and how many types of defect formation happens in laser powder bed fusion. You saw that video where everything is flying around, and you sit back and relax. You sit back and try to think about it, that how would you possibly know what kind of defects are detected by what modality? And part of the reason here is the thermal imaging, and all of these are from literature, right? And just an example, like a flaw due to a poor laser power calibration can be a good way to detect it, gets detected by thermal imaging, but thermal imaging does very poor for a flaw due to residual oxygen, for example. So you identify the modality that do the justice of the most common flaws that you could think about, right, in laser powder bed fusion. So go to the next one, and you see there are these modalities that go to the next slide. So yeah, you put these modalities inside the laser powder bed fusion system. It could be 290, 400, 300s, and we tried it on our other OEM system as well. The concept is straightforward. You pick these modalities based on their defect detection wavelength. As you see that the radiation type differs, their wavelength differs, and hence the defect detection capabilities differ. And I'll show you that in a second, how their same layout has been pictured via different modalities. And I'll go a little deeper into how each of these are helping us in the next slide. The next one, please. Yes. So EOS offers currently 4 different modalities. 3 are listed here. The other one is closed loop control. What EOS powder bed does is it is a powder bed camera of 2 megapixel. It's an off-axis mounted camera, and it takes a picture of a powder bed. It's a simple picture after exposing and after the recoating is done. What information it gives you the information that if the recoating is being done properly, if there is a part warpage, if there is a recoater striking, if there are streaks on the powder bed, that all can you detect with the optical camera. On the melt pool side, you have an on-axis mounted photodiode, which is probing at the melt pool level scenario and looking at the melt pool stability from all the photons that gets emitted and captured on the photodiode. On the exposure OT side, you have an off-axis mounted 12 megapixel SCMOS camera constantly capturing all the information from the build envelope, and it gets you the process stability from the layer wise. So you're probing now from the solidification standpoint, so from the standpoint of melt pool. And you, of course, for the purpose of qualification, you need all of these information, which can be split out as a part of quality reports. Go to the next one. Here's the fun. Yeah, you keep pressing next. You see, this is the laser. This is the on-axis EOS melt pool. The green one is the exposure OT on the off-axis side. And again, the off-axis powder bed is listed here. The off-axis ones are calibrated, and also you run correction job so that their position bias is no longer an impact to the results that you are using. And in the qualification realm, the position matters the most because all these results are at an angle which has been course corrected. But here, when you make this repetition, when you swap the new camera or new lasing system, you had to quickly run a simple job, and if it matches the baseline, I think you should be good to go. Go to the next one. What it does is the researchers have done this kind of work 10 years ago, and they gave us like, okay, my powder bed gives me these sort of streaks, swelling, short feed information, incomplete melting that you see on the first half of the image. The bottom half tells you the thermal imaging, which would be telling you the interlayer temperature right after the recoating is completed. All the exposing has done and recoating is done. Now you take the temperature of the build, and then you do the photodiode for melt pool monitoring and thermal imaging for OT for its stability. If you go to the next one, you will see here that how so I'm going to repeatedly use terminology such as gray value, and I would say mean gray value. So I want to take a moment to explain audience what do I mean by gray value. So understand, when the laser hits the powder bed, which you see on the top side from the scanner, a lot of photons gets emitted. Of course, these photons get captured by an SCMOS camera that you saw. Depending on the 8-bit or 16-bit, this camera signal, the photons that are transmitted to electrical signal gets to a certain value of the bar. If there is a 0 value, it means there are no photons emitted and there's no light. If an absolutely dark, it's no light, it's 0 value. If it's maximum value, it means it's happening, the maximum emission is happening. And you can consider it loosely to say that there's a cold part, there's a hot part in one way or the other. So you see an example for a 16-bit gray value. The scale bar is 0 to 65,500 something. And when you are exposing it, it gives you the gray value from that scale. Okay. If it's a mean, it means the mean of all the pixels of that OT mask divided by number of pixels. Okay. And that's the mean of a layer. You can have a mean of a part, so on and so forth. And these parts are of like 2000 layers or 50 layers of 700 layers, depending on how tall these parts are. Okay. Go to the next one, please. So here's how it works, right? SCMOS camera trying to look at the intensity image per layer, and I have some EOS logo here. I have some horizontal bar. I have some vertical tensile bar as well. And just to get you an example, you can extract those signatures like by just processing that particular intensity, right? So you see the green plot, the red plot, and all of that for different plots. What is on the x-axis? I know it's not visible properly, but it's a layer number, how many layers these events are happening for. And on the y-axis, you see the gray value variation. Okay, at the start, you might have a low value or a very high value, depending on what is being exposed, right? Go to the next one. And before we go and jump into the actual execution, just this is exactly the same story. If it's a lot of photons emission, it's a warm part. If it's not a lot happening, it's a cold process. Similarly, a stable or unstable process can be identified, the gray value variation and the higher standard deviation. Okay, go to the next one. The one thing I want to bring to your notice is this. The OT works with a masking technology, meaning it does mask on your CAD, on your scan area. And this needs to be perfectly aligned so that OT is capturing the photons from the proper area. On the good image on the right hand side, you see the masking on the yellow color is exactly where the where the cylinder is getting exposed, right? On the other side, there's a little bit of offset. So what it does is when you take the mean of gray value, if there's a no light, then that value suddenly becomes, very kind of different. And we have come across a few instances later on, but just be mindful that in order to have a good OT, you need to run a calibration job, and you also need to understand if the masking has been done correctly. And this is a software correction. So you just have to run one of the calibration build, and you should be able to do this correctly. Okay, go to the next one. So we start with this nominal job. This is example of a nominal job. You see on the left hand side, a simple geometry is being displayed here with a base of a rectangular cross section, the middle section of a cylinder, and the top is conical. How and why did we choose this? Arbitrarily, honestly, when you put so many sensors, you want to see the resolution of how the cross section changes are being detected by this sensor modality or not. And if so, what is the resolution of that? And that's the whole purpose of it. So we chose this, we made an 8-hour job, we made it like for 300 layers, 100 layers each for each cross section, and we did like a 60 micron. So you can understand that is how it is. It is 18 or so. Every 6 millimeter, the cross section changes, right? We laid out 142 of these on our 290, and you can see up close the scanning happened in the direction that you see in the unidirectional on the red side, red path of the laser. And go to the next one. This is where the next 30 odd slide fun begins. OT is telling me this: my intensity across the 142 samples somehow are not even, meaning some of the pockets on my bill plate is emitting more photons than the others, though I have a scanning which starts at lower left and ends at top right. My bottom right region across 100 layers each, on the left hand side you see the 3 segregation of 100 layer each for each sample combined. You see there is a pattern going on where bottom right region seems to continuously have a higher mean gray value than the other areas. Especially take a look at the top left region as well, which emits a very high gray value compared to the top right. Of course, this is an M290 machine. There is a gas flow which comes from back to front, and a recoating is happening right to left, right? So when you combine all 300 layers, this is what I see. And I thought this is an anomaly, or this is just because I ran this baseline build one time. Go to the next one. I did this 3 times. The results remain the same. You see the baseline build 1, baseline build 2, baseline build 3. All 300 layers composed of a similar behavior. This tells me something. This tells me that no matter how many times I'm going to run a job, my specimens on the bottom right are going to be always hotter or always emitting more OT value than the others. So why is the question then? It's an off-axis mounted camera. So bottom right illumination was because of the bias of the camera placement. It is placed right on when you open the 290 um, door, and you look at it, the build chamber, you'll see the position of this is upright, top right corner. There is that, and then there is a gas flow which is hindering on the top left side of it. And you can see the CFD analysis. NIST has carried out a very detailed study of similar observation, and that has to do because the grid nozzle has been utilized, which have some pocket over there which does those. So out of, go to the next one. Out of 142 samples, we labeled them from A1 all the way to X6. And here are the samples, U3, U4, S3, S4 on the top left, and all the D1s and F1s and H1s on the right-hand side, which showed me sort of a high gray value. So we need to really understand carefully that the red means bad, or green means good, or red is just okay, but it just, you have to accept the position of it. So I have to really probe into U3, U4, S3, S4, as well as some of the J6s and L6s across the build job. But I need to be certain that whatever I have derived in terms of my reasoning for it needs to be justified. So I went into a different modality. Go to the next slide. This modality is an on-axis mounted melt pool monitoring. Take a look at bottom right now. That bias is gone. There is no high gray value on the bottom right region at all. That tells me that that was because of the placement, and top left still exists. Means something is going on in the top left, which has been detected by both off axis modality and on axis modality as well. So top left is still showing me high gray value. So that is something that you need to be accounting. And that's how switching to a different modality like an on axis MPM helps you here. Okay, go to the next one. Now let's take a look at how the signature of these looks like. Before that, this is an important slide, because I told you I tried this out on 290s, 400s, and 404 as well. We used two different locations to try this concept. So one M290 at EOS and the other at the collaborator space at the Ohio State University. Take a look at two signatures of 290, which are kept next to each other. The phenomena that I identified on our M290 in Pflugerville had those spatter process instability, and it is that you see in that yellow box. On the right hand side, however, the Ohio State machine, that was not there. However, they found something very unique on the bottom left side um, of the machine, where they were having more process instability in there, which is, this tells you that there's something going on machine specific. That's how all the qualification are tied to certain machine characteristics, right? And then you cannot blindly place parts and skip their testing and all of that. And that's a part of this, that it varies machine to machine. So upon further investigating what is happening at the Ohio State, that they are getting that sort of process instability on the bottom left, we found out interestingly that their powder collecting bin, when you recoat, the leftover powder gets deposited in the collector bin, and collector bin needs to be some certain don't quote me on that, but it's something 50 should be below it. And if it's more than that, it kind of puffs the powder and puts it back on the corner. So we noticed that, and that is part of the reason. We did the similar study on 4144. We exclude this out of this discussion here, but this is the signature of 41 and 44. Of course, rotated for bringing the comparison, because the gas flow for 290 is back to front. I've rotated it for 401 and 404 just for the audience to see through. 41 seems pretty steady, and 44 as well. 44 ended with a high scan on the top right. That's how the area got illuminated more than the other. Please go to the next slide. So here you start seeing the signature. Now you ran nominal jobs. Go to the next one. You start seeing the signatures of, this is what it looks like. The background is this. No, go to the previous one. Yeah, this is the OT image. It tells you that the back watermark image is the actual sample, just horizontal way. And you see that build 1, 2, and 3 showed me some of the signatures of this part. And these are for all 142 samples combined. They look like this. At 100 layer, there is a double exposure happening. So sometime it kind of gets you on a high level. And then as you're emitting the less photons, because of change in cross section, the signature is kind of dipping down, right? And noticeably, this is the whole point of selecting this geometry, to see how the sensing is in sync with the geometry. Upon closely looking at layer number 10 to 50, we said why it is not exactly the same. And that's how you run the nominal job. You want to look at why they are not overlapping on absolutely on top of each other. And part of the reason you'll see in the next few slides, I'm going to talk about it, and it has to do with the scan rotation and all of that. So go to the next one. And here's the signature for 142 samples for the melt pool monitoring. Of course, the mean gray value has drastically different because this is a photodiode. OT is the SCMOS camera. This is a photodiode. So of course, but overall trend seems to be the similar. Of course, you see the spike at 100 layer because of the change in cross section. But again, the 10 to 50 layers were investigated, and you see the red, blue, and green line not superimposing on top of each other. That's the whole point of running the nominal jobs. Go to the next one, please. So we need to now probe, and I need to wrap this one up quickly. I need to give you enough time as well. I'm 37 minutes in. We noticed this trend, which was different in the Ohio State University machine for especially the last 100 layers for the conical cross section, because they had some mismatch on the OT, how it is capturing, and it's mean gray value, right? So it was dropping down on this behavior. So you see the layer which are good in case of our machine, the signature is fine, but as you kind of see for layer 250, sudden drop happened around 280 to 50 onwards, and that has to do with the misalign. But you can get it fixed as well. But this was how we got to identify the problem as well. Go to the next one. As I told you, I have like a 30 more slides, so we need to hurry up as well. So what I'm trying to tell you from this slide is I investigated A1. Why did I choose A1 for the first one? Because I said that is the region of a sample which had a two different OT variation between EOS and OSU sample. And you'll see in a second, I looked at A1 and I said, give me the whole first 50 to 65 layers of information on OT for three build jobs, or three A1s that we printed. And the signature of A1 tells me a different story. On the top, you see all 300 samples. On the bottom is just focusing on the layers from 50 to 65. On the right hand side, you see 53, 54, 55 layer number for build job 1, 2, and 3. They have an absolutely different scanning pattern. It has a 67-degree rotation, so not three different build job has some 67-degree rotation between them each layer. That's how your infill is differing, and hence your emission of photons vary slightly. So that difference you can see in that plot. Go to the next one. Same application of concept, but different modality. You see the same results. That variation belongs to the scan pattern. Okay, and all, of course, the position of it. If A1 trends this way, if I go all the way to U3, U4, around that, it changes slightly, but it is still having that differences as well. So go to the next one, please. So here's the example of that A1 location, and that you see the first 100 layer had a higher OT value for the OSU case than the middle 100 and the last 100, because now you keep filling out the overfill bin, right? The collection bin. So there's not a lot of thing happening there as well. So it subsidizes a little bit, but this is just to tell you that how it slice up and gets you the information at different layers, right? Go to the next one. That tells me this is very important, because now I'm locating J6 and L6 spot on the right hand side of thing, and just wanted to see how is J6 L6 for baseline build 3 looks like, and why they're not exactly the same. What does the initial spike means on the high gray value side? My logic tells me that if it's a high gray value, it's a hot pot. Because of the small particle size, it might fly here and there, as you saw in that video. It's a finicky process. It's a lot going on. So it's very hard to pinpoint these variations. But we tried getting few. So we looked at, say, layer number 57, 50, and 204, which showed me spikes. At 200 and 100, the spikes are believable. But at 204, I wanted to really see what's going on. So we looked at it and looked at OT, looked at multiple monitoring, looked at um, the other modality, and we found these things are because of the spatter and because of the small particles that are absolutely shooting up the mean gray value. Go to the next one. Here's the story. That purple signature is the mean gray value based signature for all 142 samples ran for 3 different times, right? What I'm trying to say from this is that mean value approach is not so much preferable. We need to rely on in laser powder bed fusion. There is a remelting happening for at least 5 to 10 layers, depending upon, of course, your layer thickness and what is your laser power. But you see the orange color line is more believable signature. That is the moving average of 5 previous layer history of the OT mean gray value. And that is exactly in sync with my red line. What is my red line? It is the build platform temperature. When I start the build on the right hand axis, you can see the build platform temperature. It starts at about 38 degrees Celsius preheat temperature. This material is Ti64, by the way. So it nicely increases for the rectangular cross section. It becomes steady for my cylindrical cross section, and it nicely deep down again for my conical cross section. So this gets me from the fourth modality, which is the interlayer temperature and build platform temperature, that it is in sync, and this signature do correlate with each other. Go to the next one. Now you look at all the quadrant wise signature. You split 142 samples in quadrants. You look at top left, top right, bottom right. These are all about 36 samples placed on top of each other, just to show you that this is what's going on in EOS system. The EOS M290 had a finicky top left, as I told you, the U3, U4s and all of that. And bottom left, bottom right seems to be pretty steady because they are they're away from the gas flow. And that is one of the reason why you see bottom left and bottom right being steady than top left and top right. Go to the next one. We look at the similar signature, and just one quadrant is exposed here for all 36 parts. 36 parts are below B1, B2, B3, B4, B5, D1, D2, D3 onwards. We said let's look at J6 and L6, which are marked in yellow and green, to see what those spikes are randomly, because you need to now establish the third step is what you're gonna those pink lines, the upper and lower limit. So you want to really understand all these things from that perspective. So go to the next one. What we found out, they correlate to defects. J6, L6 were really looked at closely for all modalities. For integral GV, max GV, I said, no, don't believe on mean gray value. Just give me an integral value. Give me a max value, moving average value for 1 layer, moving average for 2 layer, moving average for 5 layers, synchronous dynamics. You really probe that and you see that, okay, that's exactly what it is. It is not just the anomaly. It is at that point, that's the mean gray value being flickering because or what we discussed. Go to the next one. And now there's a side-by-side comparison between two M290s. On the left and on the right, you could see the clear difference on the black box and the bottom left box. The top left and top right on EOS is more finicky in terms of the gas flow. On the right hand side, however, the bottom left is more finicky than the top left and top right. Top right had, of course, some gas flow related issues on the OSU as well. But you can identify that those particles, from the collection bin and all of that is also kind of coming into picture. Go to the next one. Trust me, I'm gonna end soon, but this is how you do it. You run those 142 samples, you kind of place all the quadrant wide information. Now 142 samples placed on top of each other. That's the green line that is without any tolerance that you would like to see. The upper threshold, the lower threshold, this is how you can adjust your the goodness criteria, right? So next one, you'll try and see what we kind of discover from there. Go to the next one, please. Again, we did this for 4144. Not going to talk about it. Go to the next one. That's the signature. 8-bit versus 16-bit. Remember while talking about OT, I said 16-bit has 65,000 value and something. 4 ones are like, you can see how steady 4.1 is for 142 samples. You see how 4.4 is more, quadrant wise, still 8-bit, but you can do the same thing. Yeah, go to the next one. Here's that signature concept. You run nominal jobs, you come to that black reference signature, that mean gray value based on the moving average. You then start applying the 10%, 15% margin on it, depending on what kind of part are you trying to qualify. What is the safe window that you are okay with? And you have to investigate every outside spike that you see from these different modalities, right? So we did that. Next one. All right, so that U2 part was split open. I said without any post processing, we just took it off from the build plate. I said, get me the number of pores that you see through the microscopy, and we were able to get amazed that this is a signature on the top right side of the part U2 for all 300 layers, and it's a mean plus or minus sigma from its moving average signature. My choice B is to apply 3 sigma on top of it and just see what exists on the outside to see all those spike means what. If I'm qualifying this part across the bed with 3 sigma cushion, how many parts would not qualify right off the bat? So before I do that, I said there exists a fourth modality with EOS, which is a closed loop control. We wanted to try that out as well. So go to the next one. How does a closed loop control work? The regular builds that you saw had a process parameter pre-optimized. You feed it to the machine, it does its job. Smart Fusion works in a little different way. It's not a black box in any way. It's a PID controller which takes the previous layer's gray value and it adjusts the laser power. It just reduces the laser power at this point. It doesn't increase the laser power based on the value that user at the start of the job enters. Like I would say 3% variation from the nominal process parameter of 340 watts, for example. Then it would reduce laser power up to 3% of 340. And you don't put some arbitrary number that you get a keyhole porous part. So it gets to that correction factor based on looking at the gray value variation, and it reduces it laser power. It does it on a particular part, not entire layer. So you'll see that in a minute. Next video tells you on a different material in kernel 718. Go to the next one. Play this video, please. You see the standard parameter. You'll see a recoating done right now, and you'll see a standard parameter getting exposed with that 340 or 240 watt. You see a lot of interaction of powder and laser. You see the Smart Fusion, it auto corrects the laser power. Really doesn't have any afterglow, right? Next one. So what it does is it allows us to control the thermal balance of our parts. This is an example before I go to the real work that we did with this, but this just tells you that because of the controlling thermal history in a way, you don't need that much of support structure. Support structure are more difficult than just the thermal history, but in essence it is basically connecting your heat sink, which is the build plate, to that part, so that you can avoid any part lift off and things like that. But this is the core message that I'm trying to give you. So go to the next one. We ran the same build with closed loop control side by side. Baseline build 3, it's uneven distribution of U3 U4 and those areas. Same machine now turned on the Smart Fusion, and I have everything under almost similar looking but a very controlled variation around it. I have the total build time being saved by about 30 minutes. I've got layer 50 being reduced to 7 or 8 seconds. That way I can take a look at all these different layers for these samples, and I have saved some of the time that it requires because it adjusts the laser power accordingly and changes the infill scan. So go to the next one. It's a vector level control, by the way. So go to the next one. So we did split open the same U3, this time U2, and looked at what happens to the porosity and all of that. And you can see what we found, the signature, very constant, very stable, because the set gray value was like 41,000. Anything above that is not there, except layer 100, which I told you about. And it auto corrects it. So everything is now very stable. At 2 sigma, at 3 sigma choice 2, everything is almost qualifying in the case of closed loop control. So now go to the next one. You see the comparison here for that U2 part between without closed loop and with closed loop. So so now you see the amount of reduction on in these porosities, as built porosities. Go to the next one. These are not bad porosity, they are not connected or they are not linear, so it can be easily fillable with hipping process. Go to the next one. So the big question comes as, how's the signature look like? The part U2 on the left, you have a blue color signature when you don't use Smart Fusion. It is what it is behaving. We saw that across my explanation. The red one is where I set a value 41,000 as my target gray value. Anything over that pushes back by reducing the laser power. Still giving me a better part than the part that is being printed without closed loop control. So you can see side by side the same comparison of cubical, cylindrical, and conical cross section for its number of pores and the microstructure as well in the next slide. Go to the next one. So we really wanted to know, does it get me any different? This is a Ti64, so you got a lot going on there. You have alpha, beta, prior beta grain, and we can talk all about it. I need to give you some time for question answer as well. But I want to end after just two more slides. But let's get you the microstructure wise. We didn't feel any difference. Where I'm going with this is, if I can predict with my center portion of mean gray value the formation of the microstructure, that is where I'm trying to get my mechanical properties derived from. Because at least I'm printing my parts with some notion of having certain type of microstructure that is so many times would yield into certain mechanical performance. Of course, the signature would be correlated to as print status. The moment you heat treat, stress relieve, hip it, the signature has nothing to it unless everything is constant and assumed that everything was done on a single batch. Otherwise, you have control till this point. And we saw that for the hardness comparison, the dead center chart that you see with and without closed loop control. You see the red color without closed loop control all over flying, and that you see on the blue signature as well. As you see with these with the control signature, that my hardness is not varying that much as well. So go to the next one, please. So people are like, oh, this is all good. What about complex builds? Go to the next one. This is how you do it. I'm not gonna go deep into it, but remember the purple signature for all 300 layers. This is my purple signature for complex build, 54 different parts, vertical tensile, vertical fatigue, all you can think of for qualifying at very difficult aerospace component. That is my signature. My telling you this cube, my density cube gets buried inside powder bed at 230 layers. My fin cube is at some 500 layers. My UTEP complex geometry at 750 layers. But my vertical tensile stays with me till 1977 layer or something. So my thermal history throughout this, my interlayer time changes, so that oil signature is what I'm believing for. How much data does it spit out? Go to the next one. Um, how much data does it spit out? It spit out 500 gigs of data. Each modality, such as optical tomography, it's 10 frames per second. 110 gigabytes for a 1977 layer build job, 36 hours long. Melt pool monitoring close to 80 gigs. Powder bed 20 gigs. How much is actually utilized for making these signatures and all? Few GBs. It's the Excel that matters at the end of the day, right? But this is, we gotta be collecting this for your qualification. Go to the next one. That's the signature you derive for each part. And I'm going to stop right here after this explanation, that horizontal tensile fatigue stack had a good signature on the left hand side. If I just look at the signature from one modality, from the optical tomography, and we did it for 6 different modalities as well, you can see if there is any changes on the signature on the right hand side. Same stack, different build, showed me at a layer number 791 some spike. I zoomed in, I looked at it, I looked at the melt pool monitoring, I looked at OT, I looked at optical, and optical shows me part got cracked, part got wrapped during the build. So this is what it is. It is telling you that you can actually get most out of it by this multimodal approach. So where is the AI part coming in this talk? Go to the next one. I think you can skip few slides. Go to the next one. This is like build one, build two, location specific, the gas flow and all of that. Can you get out of your full screen mode and let me allow me to pick my last slide to tell them about AI, and then we can take question answers in the next 3 minutes. Just the last slide. Is it possible to no, it's way far at the end. Keep going. These are all the mechanical test results. Keep going, keep going. Yeah, one, oh yeah, one before, and one before as well, one before as well. That's me telling, not EOS telling, what are the different types of modalities we use, what are the range of defects, how important are the data, what is the cost-wise consideration. And I think OT stands out pretty good in all of these comparisons. What's not in here is fringe projections here. What is not here is eddy current based efforts that we tried as well. Go to the next one. This is where the end game is. End game with the AI is, you take a look at this right hand side data generation. You pull these samples. You have the data, but the data is off a blank. You cannot really do anything with the actual part that you extract out of it. So you need to really look at the data from the gauge length section of the tensile bar, and then you train that convolution neural network with which data, the gray value data from OT, the gray value data from melt pool monitoring, so on and so forth. And it gets you, while printing, if you see that it is 43,000 and so on and so forth, you can relate to see what could be the tensile strength and yield strength of those parts. So that is how you develop the machine learning, and that is what we are currently doing. That as you build, you generate these models that looks at all these modalities real time, and gets you that. On top of it, we are utilizing closed loop control. So we really know now that at 44, it's a good part. It's this mechanical properties. So we try to control it that way as well. All right, with that, I'll stop. And I told you that the blame is to my professorship. So keep blaming that. Thank you,
Hey,
Christy.
that's okay. Thanks, Yash. It was a great presentation. Obviously, um,
Thank you so
you've
much.
articulated why it's important to, to deploy AI, how
Yes.
to achieve faster, scalable qualification, and accelerate component qualification, which is very important, we know, to this industry. We are coming up on the end. We do have some questions for those that we didn't get to answer here. Yash will reach out to answer. This presentation will be distributed after. So I'd like to thank everybody for joining us. The one question is how many hours were on the lasers on these machines? Is that something that you can answer in our few minutes we have, or a
So
minute?
go ahead. How many lasers?
How
Or how
many hours were on the lasers on the M290 machines?
So when you say number of hours, means how many hours did we run this build job for? Is that the question?
How about we take this one? Well, it just said how many hours were on the lasers on these machines. How about we take that one offline, and we'll let you reach out directly to that particular one. So,
Okay, sure.
um, um,
What else?
what are the pressing issues in part qualification? I think you've done a great job. Is there any kind of
It's a tough one. You
final?
people are looking at part family qualification now, and there are good friends at NIAR, good friends at Department of War looking at this from a part family standpoint. They said if we can group everything on this part family, let's define the criteria for qualification of that part family, and not necessarily look at each and every part within that family. So you can apply that concept to that part family. But this is at EOS we're doing, trying to speed up the qualification burden, trying to do the in-situ inspection as we print the part, and try to be helpful to our community to not get pull out all these bars, because if you can look at the signature, if they're exactly identical, you know the reason behind it. There is no point in trying to pull these adjacent bars. So you can reduce this qualification by 50%.
That's excellent.
Yeah.
So in our couple of seconds that we have left, thank you everybody for joining us today. Yash, thank you for a phenomenal presentation. Thank you for your contribution, your membership to Lift into the industry. I'd like everybody to mark their calendars for our next one, which is Liftoff webinar, which is May 20th. So everybody have a great rest of the day. Thanks for joining us.
Thank you so much. Thank you. Bye-bye.